right, so I wanted to give you a video that you could watch that would give you a little bit of background for Gauss's law. This will be helpful to kind of get us up to speed with the things that we need to know to understand what we're doing when we're doing Gauss's law. And so in this video, I want to go into the idea of electric flux. We use the measurement of electric flux in Gauss's law, so we'll talk a little bit about that, but my primary reason, or my primary goal in this video is to help you understand what we mean by electric flux. So I did mention that electric flux is what Gauss's law is based on. And so eventually, let's just tell you what our goal is. Our goal is to eventually be able to find the electric field due to a charge distribution. That's a lot easier than those integrals that you saw in the previous chapter. So at the end of the last chapter, and also on a video, we talked about how you can calculate the electric field due to different charge distributions. Remember, there was a line, and there was a disk, and a ring. And, there's a lot of calculus, and it was kind of difficult. So Gauss's law is going to use an easier way to do this. Now, one of the things that's important is we're going to have to use situations where there's a lot of symmetry. I love symmetry. Maybe that's why I love physics, or maybe I love symmetry because I love physics. I'm not sure how that goes. But anyway, Gauss's law will work best when we have situations where the charge distribution has some sort of symmetry that we can exploit to use Gauss's law to find the electric field. Now, the definition, when you see it eventually, will have an integral, but it's okay. Don't worry about it, because in the end, you don't have to do really difficult integration in order to use Gauss's law. But let's get back to, well, first of all, in general, just to tell you what Gauss's law is all about, it's basically imagining that we surround a charge or a charge distribution by some sort of surface, and then we're going to look at the electric field that comes through that surface. So I'm trying to represent here that within this box, the cube is my surface, but inside the cube is some sort of charge distribution. And you know that charges create electric fields, and so we're actually going to do a measurement of the electric field that comes in or out of the box, in or out through the surface. And the term for that measurement is electric flux. So basically what we're going to eventually find out is that if we know how much charge is inside the surface, we can actually figure out the electric flux, but then Gauss's law, we can use that to help us figure out what the electric field is that's created by the charge. Okay, finally, we're going to get to the purpose of this video, which is understanding electric flux. So flux is a term that I think might have come up like once last semester. I'm not sure exactly if it did, but flux in physics is a term that we come across now and again. And when we're talking about flux, we're always talking about the flow of something through an area. So for electric flux, we're going to talk about electric field lines passing through some sort of area. So in this picture right here, you have that shaded area. See that little rectangle that's at an angle? That's the area. And the arrows are supposed to represent electric field lines. And when we measure electric flux, we're trying to get a sense of the number or the amount of electric field lines that go through that shaded area. Now, there's a couple things that this measurement depends on. The flux will depend on how big the electric field is, like how strong it is, and also the area. How big is the area that I'm passing through? And finally, the relative orientation of the area and the electric field. This brings up something that's kind of weird, because I don't think in the past we've associated an area having a direction. But in this case, we do have to designate a direction for the area in order to be able to figure out how those electric field lines are oriented to the area of that shaded rectangle. Okay, so the definition of electric flux, we use a capital Phi to represent electric flux, and it's a dot product of the electric field vector and the area vector. Again, here's this area vector. So how do we define it? So we're sort of imagining, and my pen's not working. So if we look at this area vector, or this area, I'm going to draw a vector, and that represents the area. But that vector is going to be perpendicular to the surface itself. Now, I did my best, but again, the way that we define the area vector is we have the surface area, but the area vector itself would of course have the magnitude of the area, but the direction would be perpendicular to the area itself. So that's how we represent the direction. Here are other pictures of just a basic surface, and notice they show you the normal vector. Remember, it's a unit vector there, that n, and so all that it defines is the direction that's perpendicular to the surface area itself. And then we see the area vector. Now the area vector is parallel to that normal, but its magnitude would be equal to the magnitude of the area of the shaded surface. You can see in this particular situation that, you know, it's really a little bit uncertain. Should we draw the area straight up or straight down, as we see over here? And for like just a single surface, that can be kind of difficult to make a definitive decision. When we talk about the area of a closed surface, that's a lot easier because the area is always going to be pointing away from the volume that's enclosed within the surface. So the area vector always goes outward. So let's look at that expression for electric flux when we're calculating it. Remember what a dot product does? A dot product is something that we can do with two vectors. We multiply them together using this dot product or scalar product. Our answer is going to be a scalar. It doesn't have a direction, it just has a magnitude. And the calculation says that it's equal to the electric field value times the area times the cosine of the angle between those two vectors. That's what theta is. So I just showed a couple different scenarios of how this might work. You know, you're going to get the greatest flux in this first picture. You can see that the area vector and the electric field vector are totally parallel to each other. And in this case, the cosine of theta, well, theta would be 0, so the cosine of 0 is 1. So the electric flux is just the electric field times the area. Let's go over to the far side because that's the other extreme. Here you see that the electric field and the area vector are perpendicular to each other. And that electric flux is 0. That actually makes sense because none of those field lines actually go through the area. They're just grazing it. And if you think about how we said the flux was defined, the flux is defined as how much of the electric field passes through the area. And so none of it does, so we don't have any flux. This is the sort of intermediate situation. And in that situation, the electric flux is just going to be equal to E times A times the cosine of theta. If you think about it, the A times the cosine of theta would just be sort of the projection of this slanted area onto the vertical, so that like how much of the area would be sort of that piece would be where the electric field lines would go straight through. But this is actually always going to be smaller than the area itself, and so we would have a smaller amount of flux in this scenario than we do right here, but more than we do in this scenario. And so that's how we calculate the electric flux. Let's just think about a little bit, why does the angle matter? You know, I find that the example of, you know, summer and winter is a good example of why the angle that the electric field lines hit the area at is crucial and helps to determine the total flux. So right now it's winter, it's really cold. Why is it cold? Well, the amount of daylight that we get is shorter. And the reason for that is that the path that the sun takes in the sky is closer to the horizon than it is during the summer months. And then that means that during the winter, when the sun is hitting the ground, it's hitting at a shallower angle because the sun is at a lower point in the sky. And so if a certain amount of energy is coming from the sun, which isn't really varying a lot from day to day, but it's coming at us at a shallow angle. So this certain amount of energy is spread out over a larger area, and so it's less efficient in heating. And so, you know, we're getting less flux from that sunlight energy, if you want to think about it. But in the summer, when the sun is higher in the sky, the sunlight hits more directly. So the energy from the sun is more concentrated. And so when it hits more directly on the actual surface, you get a more efficient delivery of energy. And so I like this analogy because it shows why, as the sort of angle between the field, we could imagine the sunlight or sun rays as being our electric field and the ground being our area. And so when there's a bigger angle between those two, you're going to get less flux than in this case when, remember, the area vector would be straight up. When they're really pretty much parallel to each other, this is going to be a greater flux. So just to sort of summarize the things that are important in calculating the flux, you know, as we look at the expression right here, you can see what makes the flux bigger or smaller. If you make the area bigger, you're going to allow more area for the electric field to pass through. So that's going to give you a greater flux. If your electric field is stronger, then that means that, and how that's going to be represented in a picture is going to be the electric field lines will be closer or more dense. So as the electric field gets stronger, the flux will get greater. And then finally, we saw that the angle between those two, treating them as vectors, will also affect the magnitude of the flux. When the electric field vector and the area vector are parallel to each other, and this can get confusing, but that means that the electric field lines are hitting the actual surface at a right angle, because remember the area vector is perpendicular to the surface of the surface area. So, but in any case, that when those two vectors are parallel to each other, you get the most flux, and it just would be reduced to E times A. If they're parallel, if the two vectors are perpendicular to each other, the electric field lines will graze the surface and they will never penetrate the area, giving zero flux. And anywhere in between, you're going to get something between 0 and the maximum amount. So those three things are going to affect the flux, the strength of the field, the size of the area, and the angle between the electric field and the area. If you don't have a uniform electric field, then you actually have to do the calculation with an integral. So you're sort of breaking up the area into small pieces, each piece of which is going to have a constant electric field. I mean, I did say if the electric field wasn't uniform, but it also could be true that maybe the direction of the area isn't constant. And so that if you have, say, a curved surface, not all the area vectors would always be pointing in the same direction, so we would break it down into little pieces and add the flux through each of those little pieces, which is essentially doing an integral. We never mentioned it yet, but the unit for electric flux is going to be the unit for electric field times the unit for area. Electric field is a Newton per coulomb, area is meter squared. So the whole unit is Newton meter squared per coulomb. It's kind of stupid conglomeration. Okay, so next time, in the next video, we'll talk about what Gauss's law is about and start to talk about how we can use it.